During prolonged fasting, hepatic gluconeogenesis increases while glycolysis is suppressed. Which of the following regulatory changes best explains this metabolic shift? Leave your answer in the comments if you think you know. One of the most important things that you need to remember about the fed and the fasting state is that the liver is oftentimes doing different things than the rest of the body is. And during the fasting state, some of the body can't use fatty acids as a fuel source, but the liver can. So right now, the liver is using up a ton of fatty acids as its main source of energy, and it's not using up any glucose. And the reason it's not using up glucose is because it's creating glucose through gluconeogenesis and sending that glucose out for parts of the body that can't use fatty acids. So this means that the liver has to have a way to not use up the glucose that it's creating before it gets sent out to the bloodstream. One of the ways that the liver achieves this is through controlling the fate of pyruvate. Here are two of the major things that could happen to pyruvate after it's made by glycolysis. It could turn into oxaloacetate, which would be the first step in gluconeogenesis. And this step is catalyzed by pyruvate carboxylase, which is activated by acetyl-CoA. The other fate for pyruvate is that it could turn into acetyl-CoA, and this is catalyzed by pyruvate dehydrogenase, which is inhibited by acetyl-CoA. So remember that we said the liver is using up a lot of fatty acids, which means it's going to be creating a ton of acetyl-CoA. So it's going to be inhibiting pyruvate dehydrogenase and activating pyruvate carboxylase. So then in the liver, we're preventing pyruvate from turning into acetyl-CoA, which would then go into the Krebs cycle, and we are promoting the conversion of pyruvate into oxaloacetate to help promote gluconeogenesis. The other way that glycolysis or gluconeogenesis is regulated in the liver is through PFK2. And PFK2 is this enzyme that takes fructose 6-phosphate and turns it into fructose 2,6-bisphosphate. Fructose 2,6-bisphosphate will then activate PFK1, which promotes this step in glycolysis and helps glycolysis go forward. However, during the fasting state, glucagon is going to lead to the phosphorylation of PFK2, which makes PFK2 act as a phosphatase and catalyze the reverse reaction. So it turns fructose 2,6-bisphosphate back into fructose 6-phosphate, which gets rid of the activation of phosphofructose kinase 1. So glycolysis loses that activation from fructose 2,6-bisphosphate, and the liver is producing a lot of ATP from fatty acid oxidation, and ATP inhibits PFK1. So glycolysis is going to slow down drastically. So we're looking for an answer that incorporates the discussion of one of these pathways. Option C is talking about how acetyl-CoA activates pyruvate carboxylase, which we talked about being a step in gluconeogenesis, so that is the correct answer. A is a correct statement because insulin does lead to higher PFK1 activity, but that's not going to lead to more gluconeogenesis. That's going to help glycolysis. B is wrong because glucagon is going to promote fatty acid oxidation in the liver, and that creates a